So, how do computers make sense of really complex networks? Things like social graphs, biological systems, or even the internet itself. The main challenge has always been translating that incredibly complicated structure into a language that a machine can actually understand and learn from.
The old way of doing things was all manual. You'd need domain experts to sit down and carefully craft features for every single node in the network. As you can imagine, this was super time-consuming, and the features you made for one network probably wouldn't work for another. But now we have something called representation learning, which pretty much automates this whole thing. The algorithm learns the important features all by itself, directly from the network structure. It's way more efficient, and it's general enough to work on all sorts of different tasks.
This is where the idea of a node embedding comes in. It's a method that takes each node in a network and translates it into a vector, which is really just a list of numbers in a lower dimensional space. The whole point is to make sure that this new vector representation captures the essence of the original network structure. Probably the best way to think about this is like creating a map. The embedding process takes the network and lays it out in a new space. And on this map, the position of every node means something. The fundamental rule is this: if two nodes were similar in the original network, they're going to be placed close to each other on this new map. And when you see this in action, the result is pretty amazing. You can take a messy, tangled web of a network that's hard to interpret and transform it into a clean, organized scatter plot. And in that plot, you suddenly see these clear clusters of points. Those clusters are the communities and the groups of similar nodes that were hiding in the network all along. Okay, so this all hinges on one really important question, right? How exactly do we decide which nodes are similar in the first place? The answer we choose here is going to define the kind of map we end up creating. Well, one really clever way to do this is by using something called random walks. The idea is actually pretty simple. Imagine taking a bunch of short, random trips through the network, starting from a particular node. The other nodes you bump into most often during these little journeys, we consider those to be similar. It's a great approach because it captures both the local neighborhood and the broader context of a node. So the process generally breaks down into 3 steps. First, the algorithm just generates thousands of these short random walks starting from every single node in the graph. Second, for each node, it makes a list of all the other nodes it visited. This collection becomes its neighborhood. And finally, the third step is to train the embeddings themselves so they get really, really good at predicting which other nodes belong in that neighborhood. Now that last step, the optimization, comes with a big challenge. If you were to do it in the most straightforward way, you'd have to compare every node with every single other node in the network for each training step. For any reasonably sized graph, that becomes computationally impossible. We're talking about a complexity that scales with the square of the number of nodes. It gets slow fast. To get around that, we use a smart trick called negative sampling. So instead of that massive network-wide comparison, the model learns a much simpler game. Can it tell the difference between its true neighbors, the positive samples, and just a handful of randomly chosen imposter nodes, the negative samples? This makes the whole process vastly more efficient and actually feasible for large networks. What's really cool is that we can also fine-tune how these random walks explore the network. We can add a bias. A walk that acts more like a breadth-first search will stick close to the starting node, giving us a micro view of the immediate area. On the other hand, a walk that behaves more like a depth-first search will wander farther away, giving us a macro view of the larger network. So we go through all this work to get these powerful vectors. What are they actually used for? Well, a ton of different machine learning tasks. You can use them for node classification, like predicting a user's interests on a social network. They're fantastic for link prediction, which is exactly how platforms recommend new friends. You can also use them for clustering to find those hidden communities, or even for graph classification, like deciding if a molecule is toxic based purely on its structure. And this idea doesn't just stop at individual nodes. You can take the same core concepts and extend them to create a single vector that represents an entire graph or even just a piece of one. One pretty direct way to do that is to first run a normal node embedding process on your graph. Then you just aggregate all those node vectors together. You could sum them up or average them out, and that gives you a single vector for the whole graph. Simple, but effective. Another slightly more creative method is to introduce a special virtual node. You add this node to your graph and create a connection from it to every other real node. Then, you just run the embedding process, and the vector you learn for that single virtual node becomes the representation for the entire graph.
Now, these random walk methods are really powerful, but they aren't perfect. There are a few key limitations to keep in mind. First, they are transductive. This just means that if a new node is added to your network after training, you can't get an embedding for it without retraining the whole model. They can also sometimes miss structural similarities. Two nodes might have the same role in different parts of the network, but their embeddings might not look similar. And finally, these methods usually only focus on the network structure, ignoring other rich features you might have, like a user's age or the type of an edge. So, to wrap it all up, the problem we started with was that handcrafting features for graph data is just too difficult and inefficient. The solution is node embeddings, which automatically learn these features by mapping nodes into a meaningful vector space. The method we looked at uses random walks to figure out which nodes are similar and then uses an efficient process to encode that similarity into the vectors. And the result? We get these incredibly versatile, task-independent features that can power all sorts of prediction tasks on graphs.